On the open plains of Earth, the atmosphere can gather enough power to reshape an entire landscape in minutes. Some tornadoes are narrow and short-lived, some are violent beyond ordinary measure, but one stands apart for its astonishing scale. Not the loudest in legend, but the widest, reliably documented tornado in the modern record. Welcome to space science. Tonight, this film follows the science, the storm, and the immense structure of the biggest tornado ever recorded on Earth. If this is the kind of deep documentary journey worth watching, please like, subscribe, and follow Space Science for more quiet explorations of extreme science and nature. Earth turns under a thin skin of air. From far above, the planet appears calm, with white cloud bands, blue ocean, brown land, and the slow curve of daylight crossing from east to west. At ground level, the atmosphere feels deep, but in planetary terms it is shallow, a delicate layer held by gravity and warmed from below and above. The sun provides the main source of energy. Land and water absorb that energy at different rates. The air responds to those differences. It expands when warmed, contracts when cooled, rises where it becomes lighter, and sinks where it becomes heavier. In this steady exchange, the broad setting for violent weather already exists, not as an exception, but as part of the ordinary work of the planet. The atmosphere is a mixture of gases, mostly nitrogen and oxygen, with smaller amounts of water vapor, argon, and carbon dioxide. Water vapor is especially important because it can change form. It can remain invisible in the air, gather into droplets, freeze into ice, and release heat as it condenses or freezes. That released heat is called latent heat, meaning heat stored during a change of state. Once defined, it remains simply a hidden source of warmth inside cloud and storm. Even before any storm appears, the capacity of air to hold moisture shapes how strongly it may later rise. Warm air can hold more water vapor than cold air. This simple fact helps create strong contrasts across large regions of the world. The lower part of the atmosphere, where everyday weather forms, is the troposphere. It extends from the surface upward to a height that varies with latitude and season. Within this layer, temperature usually decreases with height. This common pattern matters because air that rises into a colder surrounding environment may stay warmer than the air around it. If it does, it keeps rising. If it cools too much, it slows and may sink again. The balance between rising and sinking is central to weather. Stable air resists vertical motion, unstable air supports it, on quiet days. That balance produces drifting clouds or none at all. On severe days, it supports towering clouds that grow through a great depth of the troposphere. The sun does not heat Earth evenly. The equatorial regions receive more direct sunlight across the year, while the poles receive less. Seasons shift the pattern north and south. Day length changes. The angle of sunlight changes. Snow, soil, forests, grass, rock, and ocean all respond in different ways. Water warms slowly and cools slowly. Dry ground warms and cools more quickly. A snow-covered surface reflects much of the sun's energy. Darker land absorbs more. These contrasts create temperature gradients, which are changes in temperature across distance. The atmosphere responds to those gradients by moving heat around. Winds form because air flows from regions of higher pressure toward regions of lower pressure, while Earth's rotation bends that flow. That bending effect is often called the Coriolis effect. On the rotating planet, moving air does not travel in a perfectly straight path over long distances. In the northern hemisphere, it tends to curve to the right of its motion. In the southern hemisphere, it tends to curve to the left. This does not create storms by itself, but it helps shape the larger circulation of the atmosphere. Broad belts of wind emerge. Jet streams form high above, where strong temperature contrasts help produce narrow corridors of fast-moving air. These upper winds matter because they help organize the lower atmosphere beneath them. They also help carry weather systems across continents, linking distant regions of cold, warmth, dryness, and moisture into one moving pattern. The atmosphere is never still. Even under a clear sky, it contains waves, eddies, pockets of mixing air, and layers sliding past one another, near the surface. Friction slows the wind. Higher up, the flow may become faster and smoother. This change of wind speed or direction with height is called wind shear. It is one of the most important ingredients in severe storm environments. At the planetary scale, wind shear appears naturally because the ground interacts with air differently from the free atmosphere above, and because temperature contrasts vary with height and distance. A calm morning at the surface can exist beneath powerful winds aloft. The quietness near the ground does not mean the sky above is simple. Moisture also varies greatly across Earth. Some regions sit beneath dry descending air much of the year. Others lie near warm seas that constantly feed water vapor into the lower atmosphere. When moist air moves inland and meets cooler or drier air, the contrast can become sharp. The atmosphere stores these differences. It does not remove them at once. It carries them, reshapes them, and sometimes stacks them into layers. A warm, moist layer may spread beneath a dry layer. A cool layer may undercut both. Such arrangements can persist for hours or days. The sky may still look ordinary while the air grows more ready for sudden vertical motion. Clouds make some of these hidden processes visible. Thin, high clouds show moisture and wind in the upper atmosphere. Flat, low clouds show stable layers near the surface. Tall clouds reveal rising motion. Yet much of the atmosphere remains invisible, and its structure must be inferred from measurements. Weather balloons rise through it and record temperature, humidity, pressure, and wind. Aircraft sample parts of it. Satellites observe cloud tops, water vapor patterns, and broad temperature fields. Radar reveals precipitation once clouds produce raindrops or ice. Together, these tools show that severe weather does not begin at the ground and does not begin inside one cloud. It develops within a larger environment shaped by the entire lower atmosphere and by forces extending from the surface to high altitudes. Earth's surface adds further texture to this picture. Plains, forests, mountains, coastlines, and deserts affect how quickly air warms, cools, and moves. A mountain chain can redirect broad airflow and help separate dry regions from moist ones. A warm body of water can feed moisture inland over long distances. Flat open land can allow air masses to travel with fewer barriers. None of these features acts alone. The atmosphere responds to all of them at once, integrating sunlight, moisture, terrain, and rotation into constantly shifting patterns. Some days the result is gentle rain. Some days it is dry wind. Some days the pattern becomes favorable for the strongest rotating storms known on Earth. At the broader scale, then, a great tornado is not an isolated event. It belongs to a chain of conditions that begins with ordinary planetary processes. Sunlight falls unevenly. Land and water answer differently. Air warms, cools, rises, sinks, bends, and flows. Moisture gathers and is carried. Fast winds develop high above slower winds below. Stability weakens in some places and strengthens in others. The atmosphere builds contrasts across space and time. A violent storm day is one outcome of this restless balance. The open sky over Earth contains all the necessary materials long before any cloud begins to tower. In that wide outer setting, the story remains one of moving air, stored heat, and a planet that never truly rests. North America holds a broad interior that opens toward the sky. From the Gulf of Mexico in the south to the Canadian prairies in the north, and from the Appalachian Mountains in the east to the Rocky Mountains in the west, the land forms a wide passage for moving air. This shape matters. A continent can block, divide, or mix air masses depending on its mountains, coastlines, and plains. In central North America, the arrangement is unusually favorable for strong contrast. Warm, humid air can travel far inland from the south. Cool, dry air can descend from higher latitudes. Dry, elevated air can spread eastward from the interior west. These different bodies of air do not remain in their places. They move across one another and beside one another over a landscape that allows long reach and limited obstruction. The Great Plains are central to this setting. They stretch in a broad band along the eastern side of the Rocky Mountains, running through parts of Texas, Oklahoma, Kansas, Nebraska, South Dakota, and farther north into Canada. The land is not perfectly flat. Yet compared with mountainous or deeply broken terrain, it offers a wide and open surface. Grasses, cropland, river valleys, and gentle rises dominate much of the region. The gradual slope rises westward toward the high plains. This broad incline does not stop airflow. Instead, it helps define how near-surface air spreads and deepens. Air can move over these plains in long fetches, gathering warmth or moisture from the surface below, or retaining the character it brings from distant source regions. To the south lies the Gulf of Mexico, a warm body of water that acts as a vast reservoir of moisture. Water evaporates from its surface and adds water vapor to the lower atmosphere. When winds are favorable, this warm, humid air streams northward into Texas and beyond. Because water changes temperature more slowly than land, the Gulf remains an efficient moisture source through much of the warm season and often into cooler parts of the year. This moisture does not merely make the air feel heavy, it changes how much energy a storm may draw from rising air. Humid air near the surface often means that when parcels of air rise and cool, cloud forms more easily and hidden heat is released. Over the plains, access to Gulf moisture is one reason severe thunderstorms can become so intense. To the west rise the Rocky Mountains. Their height interrupts the atmosphere from the surface into the middle troposphere. Air approaching or passing over the mountains changes in pressure, temperature, and moisture. Some air is forced upward, cools, and loses moisture. Some descends on the eastern side, warming and drying as it sinks. This descending air helps create dry regions across the interior western high plains. The mountains also shape larger wind patterns. They help separate the moist low-level influence of the Gulf from the drier air masses of the plateau and desert regions farther west. In addition, they guide upper-level flow and influence the development of lee cyclones, areas of lower pressure that often form east of mountain ranges. A lee cyclone is a low-pressure system that develops on the downwind side of high terrain. Once defined, it remains simply a pressure center that helps draw air together and sharpen regional contrasts across the plains. Southwest of the Central Plains lie arid and semi-arid lands, including parts of northern Mexico, New Mexico, and the high plateaus farther west. These regions are important not because they often produce the strongest tornadoes themselves, but because they supply dry air that can spread above or alongside moist air from the Gulf. The dry air is often warm at mid-levels and can act like a cap, a layer that suppresses rising motion beneath it for a time. Near the surface, other dry air masses can advance eastward and meet moist air in a sharp boundary. This dry continental influence is part of the continental architecture. It adds contrast, depth, and layering to the atmosphere over the plains. Far to the north and northwest, cooler air forms over higher latitudes and across the interior of Canada. In some seasons, this air is very cold and dry. In spring, it may still be cool relative to the warming plains farther south. These cooler air masses can move southward or southeastward behind frontal systems. When they meet warm, moist air over the central United States, the contrast can become strong. The meeting line may stretch across many hundreds of kilometers. Yet the broad geography is what makes such meetings common. Few major east-west mountain ranges block north-south exchange in the center of the continent. Air can travel large distances with its character partly preserved, especially when guided by pressure systems and upper winds. The Mississippi River basin and its surrounding lowlands also matter. They do not act like a mountain barrier or ocean reservoir, but they form a large connected interior through which moist air can flow. The terrain east of the Great Plains becomes more wooded, more varied, and gradually more confined by the Appalachians. Even so, the lower central United States remains open enough for warm, humid air to spread inland with remarkable reach. In spring and early summer, this northward moisture return often deepens from Texas into Kansas and beyond. The process can happen after cold season air has retreated, rebuilding warmth and humidity near the surface over a very large region. The plains also experience strong seasonal change. During winter, the land cools sharply, and cold air masses often dominate large areas. During spring, the sun climbs higher, the surface warms faster, and contrast increases. Warmth pushes northward from the south, while cooler air still lingers or returns from the north and west. This transitional season is especially important for severe weather, because it often places large temperature and moisture differences in close reach of one another. Summer brings continued heat and humidity, though the exact corridor of strongest contrast can shift northward. Autumn reverses some patterns, yet severe storms can still occur where warm, moist air meets approaching cooler systems. The geography does not change, but the seasonal distribution of heat and moisture shifts across it. One of the most notable features of the region is how little it shelters the air from long-distance travel. In other parts of the world, mountain chains or cold oceans may limit direct interaction between warm, moist tropical air and cool continental or polar air. In central North America, that interaction is unusually efficient. A person standing on the plains may see only local grass, road, fence, and horizon, yet the air overhead may contain influences from sea, desert, mountain, and high latitude all at once. The land permits a kind of atmospheric meeting ground. That meeting ground is not permanent at one point. It shifts from day to day, but the continental layout keeps recreating it. The result is a storm corridor known informally as Tornado Alley, though the reality is broader and more complex than a single narrow belt. Tornadoes occur in many regions, including the southeastern United States and other parts of the world. Still, the Central Plains remain famous because the geography repeatedly supports the kind of storm environments that can produce long-lived supercells and some of the most violent tornadoes observed. This is not because the land itself spins the air. It is because the land and nearby waters arrange the ingredients, allowing warm, humid air, dry, elevated air, and cooler air to approach one another under favorable winds. The continent provides the stage in a physical sense, not a dramatic one. It shapes motion, storage, contrast, and access. Across this wide middle of North America, geography works slowly and constantly. The Gulf offers moisture, the plains offer openness, The Rockies offer separation, descent, and pressure changes. The north offers cooler air, the southwest offers dry air. The seasons shift their boundaries, but the arrangement remains. From this broad shape of land and water, the atmosphere inherits pathways. Those pathways guide where severe storm days become most likely, where air masses meet most sharply, and where the open sky over the plains can gather unusual power. Across the central plains, the atmosphere gathers itself into broad air masses. An air mass is a large body of air with similar temperature and moisture through much of its lower depth. Once it forms over a source region, it carries some of that region's character as it moves. Over North America, several of these broad air bodies often approach the plains at the same time. They do not arrive as clean blocks with sharp edges everywhere. They stretch, thin, deepen, and mix. Yet each still keeps enough identity to shape severe weather. Before any violent tornado can form, these wider reservoirs of air must first occupy the same country. From the south comes maritime tropical air, warm and humid air that forms over the Gulf of Mexico and nearby warm waters. It is rich in water vapor, often deep in the lower atmosphere, and usually moves northward on southerly winds. Near the ground it feels heavy, soft, and mild, especially after sunset when dry inland places cool more quickly. This air mass matters because moisture is not a small detail in storm development. It affects cloud base height, the amount of heat released when vapor condenses, and the buoyancy of rising air. Buoyancy is the tendency of lighter air to rise through heavier air. Once defined, it remains simply the upward push that allows warm, moist parcels to keep climbing. On severe weather days, maritime tropical air supplies much of that upward potential. As this warm, humid air travels inland, it changes. It may pass over fields, rivers, towns, and dry ground. During daytime it warms further near the surface. At night it often continues moving north in a low-level jet, a corridor of faster wind a short distance above the ground. This nocturnal strengthening helps transport moisture far inland, sometimes rebuilding humid air over the plains after daytime mixing has thinned it. The low-level jet does not create instability on its own, but it deepens and refreshes the moist layer. In the central United States, this transport is one reason rich low-level moisture can appear surprisingly far from the coast. From the west and southwest comes a very different air mass. This is continental tropical or desert-modified air, hot and dry near the surface in some settings, and often associated with elevated mixed layers aloft. An elevated mixed layer is a deep layer of warm, dry, well-mixed air that forms over high, dry terrain and spreads eastward above cooler or moister air near the surface. Once defined, it remains simply a dry layer above the lower moist air. This layer is important because it can act as a lid. Meteorologists often call that lid a cap, a layer that suppresses early rising motion by keeping warm air above cooler surface parcels. On many severe weather days, the cap prevents scattered weak storms from forming too soon. As a result, energy can accumulate in the moist air below. If the cap later weakens or is breached along a boundary, the storms that break through may grow rapidly and become more organized. This dry western influence also sharpens contrast. Near the surface, dry air from the high plains and plateau regions can press eastward, while humid Gulf air presses northward and westward. Where they meet, the difference in moisture can be striking, even when temperature changes little across a short distance. The sky may look clearer on the dry side and hazier on the moist side. Plants, soil, and visibility often differ as well. The air itself becomes arranged in horizontal contrast, with humidity pooled in one corridor and dryness in another. These contrasts prepare the lower atmosphere for more focused lifting and stronger local gradients. From the north and northwest comes continental polar air, cooler and usually drier air formed over higher latitudes in the interior of Canada. In winter, this air can be intensely cold. In spring, it is often only relatively cool compared with the increasingly warm plains farther south. Even that difference matters. Cooler air is denser. It tends to undercut warmer air when the two meet. As polar air advances southward behind a front, or lingers over northern areas while warm humid air expands northward beneath strengthening spring sunlight, the plains become a meeting zone of unlike air masses. The cool air may not always dominate the full depth of the lower atmosphere. Sometimes it arrives in shallow form near the surface. Sometimes it occupies a deeper layer. The exact depth changes how storms later draw in air near the ground and how stable or unstable the environment becomes. There is also maritime polar air in some situations, cooler moist air modified by passage over northern oceans or the Pacific coast before crossing land and mountain barriers. By the time it reaches the interior plains, much of its original maritime character may be altered. Yet it can still contribute to larger weather systems and frontal structure. In many severe storm setups, however, the most important contrasts are those between Gulf moisture, dry western air, and cooler continental air from the north. These three influences do not need to arrive equally. One may dominate a broad area while another appears only in a narrow corridor or elevated layer. What matters is their coexistence and the way they stack and spread across the region. Air masses are not only different in temperature and moisture, they also differ in depth and vertical structure. A shallow, cool air mass near the ground can sit beneath warmer air above. A deep, moist layer can extend upwards several kilometers, or it can remain trapped close to the surface beneath dry, mid-level air. These layered arrangements are crucial. Severe thunderstorms often depend not just on what air is present, but on how that air is arranged from the ground upward. A humid surface layer beneath an elevated mixed layer can hold large potential energy. A cool surface layer beneath warmer air may create stability and suppress storms entirely. The same broad air masses can produce very different weather depending on their thickness, motion, and overlap. The boundaries between these air masses are rarely motionless. Southerly flow may strengthen through the day and push moisture northward. Daytime heating can deepen the mixed dry air west of the moist corridor. A passing weather disturbance high above can encourage pressure falls at the surface, drawing air together from several directions. In this way, the broad air masses behave like slow rivers of atmosphere. Their edges shift across counties and states. Their depth change between morning and evening. They may retreat for a day and return the next. Severe weather forecasts depend on tracking these changes, because a small shift in the position of rich moisture or shallow cool air can change where the strongest storms become possible. Observations show these air masses through measurements rather than through sight alone. Surface stations record temperature, dew point, pressure, and wind. Dew point is the temperature to which air must cool for saturation to begin, and it serves as a practical measure of moisture content. Once defined, it remains simply a way to estimate how much water vapor the air contains. Weather balloons reveal where the moist layer ends, where dry air begins, and how temperature changes with height. Satellite data show broad moisture plumes and dry intrusions. On maps, the atmosphere begins to look less like empty space and more like a layered terrain of invisible material. Before a supercell forms, before a wall cloud lowers, before a tornado touches the ground, these large air masses already determine much of what is possible. Warm, humid air offers fuel. Dry, elevated air controls timing and structure. Cooler polar air adds contrast and density. Over the plains, they come into reach of one another again and again. Their meeting is not yet a storm. It is a condition, a wide atmospheric arrangement stretched across a continent. In this outer stage of the process, the air remains broad, patient, and slow-moving in human terms, yet full of stored difference. That difference is the raw material from which the day's sharper boundaries later emerge. Across the plains, the broad air masses do not blend evenly. They meet along boundaries, long zones where temperature, moisture, wind, or all three change across a relatively short distance. These boundaries are not walls, they're bands of transition, sometimes broad, sometimes narrow, always moving or changing shape. On weather maps they appear as lines because the atmosphere must be simplified to be understood. In reality they are layered structures with depth, tilt, and irregular edges. Before a violent tornado day becomes visible in clouds and rain, much of its character is already present along these lines of separation. A cold front is one of the most familiar boundaries. It forms where advancing cooler air displaces warmer air. Because cool air is denser, it tends to wedge beneath warm air, forcing the warmer air upward. This upward motion is important. Air does not need to rise freely on its own if a front can push it upward. The lift may begin gently across a broad zone or more sharply along a narrow leading edge. Behind the front, temperatures usually fall and winds often shift. Ahead of it, warm, moist air may remain in place until the frontal zone arrives. Cold fronts connected to strong spring systems often sweep southeastward across the plains, helping organize thunderstorms where other ingredients are already waiting. A warm front is different. Here, advancing warm air glides over cooler air already near the surface. Because the cool air is harder to dislodge, the warmer air often rises gradually over it, producing layered clouds and widespread precipitation in many situations. Yet on severe weather days, a warm front can become especially important because it marks a zone where surface winds, moisture, and temperature may change sharply over short distance. Along and just south of the boundary, low-level winds can become more backed, meaning they blow more from the east or southeast rather than from the south or southwest. Once defined, backed winds remain simply winds turned more against the usual west to east flow. This matters because it increases turning in the lower atmosphere, which later supports stronger storm rotation. Warm fronts are not always dramatic to the eye, but they can be among the most significant severe weather boundaries. Another major boundary of the plains is the dry line. Unlike a cold or warm front, the dry line is defined mainly by a sharp change in moisture rather than temperature. To one side lies warm, humid air from the Gulf of Mexico. To the other lies much drier continental air from the west. Temperatures on the dry side may even be higher, especially during daytime heating, because dry air warms efficiently. What changes most strongly is dew point, cloud character, haze, and the feel of the air itself. The dry line often forms across western Texas, Oklahoma, Kansas, and nearby areas when moist low-level flow from the south presses against dry mixed air from the high plains. During the day, the dry line can sharpen as dry air mixes downward and eastward. By evening it may retreat westward as surface cooling weakens the mixing. It is not a fixed line. It breathes with the daily cycle. The dry line matters because it is both a boundary and a trigger. Humid air near it is often capped by warm, dry air aloft. Surface heating continues. Moisture pools, winds converge, meaning they flow toward each other and force air upward. Even modest upward motion along the dry line may be enough to break the cap in isolated places. When that happens, storms can rise explosively into an environment that has been protected from earlier, weaker convection. Convection is vertical heat-driven motion in the atmosphere, often expressed in rising thermals and storm updrafts. Once defined, it remains simply rising air that carries heat and moisture upward. Along the dry line, convection often begins in scattered form rather than in a continuous line, and that scattered character can favor individual rotating storms instead of a broad squall line. Outflow boundaries add further complexity. These form when rain-cooled air from existing thunderstorms spreads outward along the ground. The leading edge of that cooler air behaves somewhat like a miniature front. It lifts warmer air ahead of it and can become a focus for new storm development. Outflow boundaries are often subtle. They may be marked by a wind shift, a narrow line of a low cloud, or a sudden change in temperature and humidity. Because they are produced by earlier storms, they carry a memory of prior convection into the day's later atmosphere. A severe storm environment is rarely built from a single clean feature. Instead, old storms may leave behind boundaries that interact with new moisture, heating, and wind fields, creating pockets of enhanced risk. There are also stationary fronts, where neither air mass advances strongly, and occluded fronts, which occur in more mature low-pressure systems when a cold front overtakes a warm front. These can matter, but on the plains the most critical boundaries for classic violent tornado environments are often the dry line, warm front, cold front, and smaller remnant outflow zones. Their exact placement determines where lift is strongest, where moisture is deepest, where winds turn most with height, and where storms stay discrete rather than merging too quickly. The atmosphere near a boundary is not uniform from bottom to top. A front may slope upward with height, placing cool air at the surface and warmer air above farther poleward. A dry line may be sharp at the ground but more diffuse above, or it may be tied to deeper dry air that overruns moist surface flow. These vertical arrangements matter because a storm draws air from a range of levels. A boundary may seem minor at the surface yet strongly alter the air a storm ingests. For example, air just east of a dry line may have high moisture near the ground and relatively dry air above, supporting strong buoyancy if lifted. Along a warm front, a storm may ingest cooler, stable air on one side and warmer, more unstable air on the other. The result can be a highly variable storm environment over very short distances. Boundaries also change the wind field. As pressure patterns tighten and surface heating changes the depth of the boundary layer, winds may shift from south to southeast east of a dry line, from east to northeast north of a warm front, or from southerly to westerly behind a cold front. These turns are important because strong storms respond not only to how fast the wind blows, but also to how it changes direction with height. A boundary can locally increase that turning, making one county far more favorable for rotation than another nearby county with similar temperature and humidity. In this way, boundaries focus the atmosphere. They concentrate ingredients that at larger scale remain spread across the plains. Meteorologists study these lines carefully because their position is often uncertain by a modest but important amount. A dry line may mix eastward faster than expected. A warm front may lift north more slowly. Morning clouds may delay heating south of one boundary but not another. Thunderstorms developing upstream may lay down fresh outflow by midday. These details affect where the strongest updrafts can first route near the surface. They also affect whether storms remain isolated long enough to organize. A violent tornado environment is often narrow in space even within a broad, severe weather day, and boundaries are one reason why. At this stage, the atmosphere is still arranging itself. No single storm yet dominates the landscape. The key process is separation becoming contact. Moist air pushes against dry air. Cool air lies beside warm air. Old storm air undercuts fresh inflow. Winds gather and turn along invisible edges. The plains hold these boundaries for hours, sometimes for much of a day, while heat, moisture, and pressure slowly alter them. Along these lines, the air is prepared to rise more easily than elsewhere. The broader air masses have now narrowed into zones of interaction. In those zones, the day's hidden structure becomes sharper, more local, and more ready to support the first sustained storm growth. By the time a violent tornado day fully develops, the atmosphere over part of the plains has become finely arranged. The large air masses are already in place. The boundaries between them have sharpened. Now the concern is no longer the broad geography of the continent or the slow movement of seasonal air reservoirs. It is the condition of the atmosphere across one day, often across only a few hundred kilometers, sometimes across much less. Within this region, the air near the ground may be warm and humid. The air above may be dry and somewhat warmer than expected, and the winds may strengthen and turn steadily with height. A day primed for violence is not defined by one single extreme value. It is defined by a particular balance of ingredients acting together. One of the most important ingredients is instability. In weather science, instability means that if a parcel of air is lifted, it will continue to rise on its own because it remains warmer than the air around it. This warmth does not need to be large. A small temperature advantage is enough if it persists through depth. Warm, moist air near the surface is especially effective because as it rises and cools, water vapor condenses into cloud droplets. That condensation releases hidden heat into the parcel, helping it remain buoyant. On a severe weather day, the lower atmosphere often holds deep moisture from the Gulf, while strong daytime heating raises surface temperature further. The result can be a large reservoir of potential upward motion. Meteorologists often describe this stored energy with a quantity called convective available potential energy. Once defined, it can remain simply a measure of how much upward acceleration rising air may gain if it is free to rise. High values indicate that the atmosphere can support vigorous updrafts, the rising currents inside thunderstorms. Yet high instability alone does not guarantee a violent tornado day. Many hot and humid days produce only scattered showers, ordinary thunderstorms, or no storm at all. The energy must be accessible. The atmosphere must offer a way to start the lift and a structure that allows the storm to remain organized rather than collapse into rain and downdraft too quickly. That is where the cap becomes important. Earlier in the day, a layer of warm air above the surface may suppress storm growth. Rising parcels from the ground cool as they rise. If they encounter a layer that is warmer than they are, they lose their upward advantage and stop. This can prevent weak, messy storms from forming too early across a broad area. On days that later produce strong tornadoes, the cap is often present during the morning or early afternoon. It stores the instability beneath it. Surface heating deepens the warm, humid boundary layer. Moisture transport continues. Pressure falls near a dry line or low-pressure center strengthen convergence. The atmosphere becomes loaded, but still quiet in appearance across many places. Lift is the next ingredient. Air must be pushed upward enough to reach the level where it can rise freely. Lift can come from a dry line, a cold front, a warm front, an outflow boundary, or more subtle sources such as rising motion linked to a disturbance aloft. It can also come from local convergence where winds flow together near the surface. On a violent tornado day, the best area is often one where lift is strong enough to break the cap in a few places, but not so widespread that storms erupt everywhere at once. If too many storms form early, they may compete for warm, moist inflow, merge into clusters, or produce broad areas of rain-cooled air that disrupt the environment. The most dangerous setup often favors a small number of intense storms rather than a crowded sky. Moisture near the ground shapes more than storm strength. It also affects the height of the cloud base. When the air is humid, condensation begins after less cooling, so cloud bases tend to form lower. Lower cloud bases are important because they reduce the distance between the rotating part of the storm near the cloud base and the ground. They also influence the temperature and buoyancy of the air entering the storm. Observations indicate that environments with rich low-level moisture and relatively low cloud bases are more favorable for strong tornadoes. Though this is one factor among several and not a rule by itself, some violent tornadoes form with somewhat higher cloud bases, and many storms with low cloud bases never produce tornadoes. The atmosphere remains selective. Wind shear is another central ingredient. Wind shear is the change in wind speed or direction with height. On a dangerous tornado day, surface winds may blow from the southeast or south, while winds higher up turn more southerly, then southwesterly, and often become much faster. This means that rising air inside a storm encounters different winds as it climbs. The storm tilts and separates its updraft from its rain-cooled downdraft, helping it survive longer. At the same time, the turning of the wind with height allows horizontal rotation in the environment to be tilted into the vertical. Strong low-level shear is especially important. It gives the storm access to streamwise vorticity, a technical term for spin aligned with the incoming flow. Once defined, it may remain simply environmental spin that the storm can ingest and tighten. The winds above also matter. A strong current in the middle and upper troposphere helps ventilate the storm, carrying air and precipitation away from the updraft so the storm does not choke on its own rain. It can also strengthen rising motion over a larger region if the storm environment lies beneath a favorable part of a jet streak, a local maximum in jet stream speed. When upper-level support is present, surface pressure may fall more efficiently, convergence may increase, and the large-scale background becomes more supportive of sustained severe storms. Still, a violent tornado day does not always require an exceptionally powerful jet overhead. The key is the full vertical profile, not one layer in isolation. Temperature contrast in the vertical is also important. Cool air in the middle levels over warm moist air near the surface increases lapse rates, the rate at which temperature decreases with height. Steep lapse rates favor instability because a rising parcel cools more slowly relative to its environment. Elevated mixed layers from the high terrain west of the plains often provide exactly this structure: dry, warm air aloft, but with steep lapse rates beneath that dry layer. Combined with moisture below, the result can be explosive buoyancy once the cap is breached. On such a day, the atmosphere often appears ordinary to casual observation through the morning. Thin high clouds may pass overhead. Low clouds may thin or break. Surface winds may become more insistent. The air may feel increasingly warm and moist. Forecast soundings, radar, satellite, and surface maps reveal a more complex picture. Moisture deepens, a boundary sharpens, winds strengthen at multiple levels. Small cumulus clouds begin to form where heating and lift are strongest. Most of them flatten and fade beneath the cap. A few persist. The difference between an ordinary tower and a sustained storm is small at first, yet the environment has already chosen which kind of growth is possible. A day primed for violence is therefore a day of alignment. Instability is large but still contained. Lift is focused but not too widespread. Moisture is deep near the surface. Cloud bases are not excessively high. Lapse rates are steep. Wind shear increases and turns through depth. The atmosphere is neither too stable nor too chaotic. It sits in a narrow balance that supports strong, isolated, rotating storms. No tornado exists yet. Even the parent thunderstorm may still be forming. But the outer environmental work of the day is now complete. The air over one part of the plains has become capable of sustaining a supercell, a storm with durable internal rotation. In that prepared atmosphere, the first tower that breaks free can begin to organize itself around the wind. The first storm that breaks through the cap does not become important at once. At first, it is only a growing tower of cloud, a deep column of rising air carrying warmth and moisture upward. Countless such towers form and fade across many warm seasons. Most remain ordinary thunderstorms. They rise, produce rain, and perhaps hail, then weaken as their own rain-cooled downdraft undercuts the source of warm inflow feeding the updraft. The life of an ordinary thunderstorm is often short because the storm interferes with itself. On the most dangerous tornado days, however, one storm may find an environment that allows a different outcome. It becomes a supercell, a thunderstorm whose updraft rotates in an organized and persistent way. A supercell is not defined only by size or by violence. It is defined by structure. The storm forms within an environment of strong instability and wind shear. Rising air begins to lean with the wind rather than climbing straight upward. Rain and hail fall away from the strongest upward current instead of dropping directly into it. This separation matters greatly. The storm preserves a cleaner intake of warm, moist air near the ground while sending precipitation and cooler outflow into other parts of its circulation. In simple terms, the storm becomes less self-destructive. It gains the ability to persist for hours rather than minutes, sometimes moving across great stretches of the plains while maintaining a recognizable internal arrangement. At the heart of the supercell lies the updraft, the main rising column of air. It is strong because the atmosphere is unstable, and it is sustained because the environment continues to feed it. Warm, humid air streams inward near the surface. As that air rises, water vapor condenses into cloud and releases hidden heat. This keeps the updraft buoyant. Around the updraft, precipitation forms as droplets grow, freeze, and collide with ice particles. Hail may develop in repeated cycles within the storm, carried upward again and again before becoming too heavy to remain suspended. The storm is therefore not only a rising plume, it is a complete system of ascent, descent, growth of precipitation, and exchange with the surrounding air. The key difference is rotation. In the sheared environment, the storm begins to acquire spin that becomes organized on the scale of the updraft itself. The rotation is not yet the tornado. It is much broader and occupies a large portion of the storm. This rotating updraft helps stabilize the storm's internal structure. It affects pressure, airflow, and the placement of rain and hail. The storm begins to exhibit persistent regions rather than random bursts. Its forward flank, usually on the side toward which it moves, often contains heavy precipitation and hail. Its rear flank may contain a different downdraft region wrapping around part of the updraft. Between these sectors, warm inflow continues to feed the storm at low levels. The appearance of a supercell often reflects this organization. Beneath the higher anvil cloud, the storm may show a broad rain-free base in the area of strongest inflow, especially where the lower air is relatively dry enough to delay visible condensation. Nearby, curtains of rain and hail may hang from the forward flank. The cloud tower itself can appear sharply sculpted because strong rising motion and rotating flow maintain a coherent form. Yet the storm is not static. It is always renewing itself, drawing in fresh air, shedding precipitation, and moving through an environment that continues to evolve beneath it. The anvil spreads outward high in the storm where rising air reaches stable layers near the top of the troposphere and can no longer continue upward freely. Winds at those levels often stretch the icy cloud shield downstream. This broad anvil is the visible expression of deep ascent. But the more important processes remain lower, where the storm is anchored to the warm, moist boundary layer. A supercell survives because its low-level inflow remains connected to the updraft. If rain-cooled air spreads too far into that inflow, the storm may weaken or change character. If the inflow remains rich and undisturbed, the rotating updraft can persist and intensify. Supercells may appear in more than one form. Some are classic, with a balanced structure and a visible rain-free base alongside a distinct precipitation core. Some are high precipitation supercells, wrapped in so much rain that parts of the circulation become hidden. Others are low precipitation storms, with less visible rainfall and a more exposed structure, often in somewhat drier environments. The storm most often associated with strong tornadoes is the classic or high precipitation type, in an environment rich in low-level moisture and strong shear, though violent tornadoes can occur in more varied settings. What matters is not the label alone, but how the storm manages the arrangement of its inflow, rotation, precipitation, and downdrafts. The storm's path also matters. A mature supercell often deviates from the mean flow rather than simply drifting with the average wind. In many Northern Hemisphere cases, it turns to the right of the broader storm motion. This right-moving behavior is linked to the rotating dynamics of the storm and helps maintain access to the most favorable inflow. A left-moving partner can sometimes form as well, especially from an initial splitting storm, but the right-moving storm usually becomes the dominant tornado producer in classic Great Plains environments. This motion is another sign that the storm has become a dynamic entity with its own organized circulation rather than a passive cloud carried along by the wind. Inside the supercell, updraft and downdraft are both necessary. The rising current builds cloud, precipitation, and rotation. The downdrafts, formed by cooled air, melting, evaporation, and drag from falling precipitation, shape the lower part of the storm. They help carve the storm base and reorganize airflow near the ground. Yet at this stage, the supercell remains a storm-scale system. The rotating updraft is far broader than a tornado. The air below the storm base is still being arranged, with inflow streaming inward and downdraft air wrapping around in different sectors. The balance between these flows will determine whether the lower circulation tightens or remains broad and elevated. Meteorologists identify supercells through radar as well as by visual structure. Doppler radar often reveals a rotating pattern in the storm, with winds moving toward and away from the radar in close proximity. Reflectivity patterns may show a hook-shaped appendage where precipitation wraps around the rotating updraft. These signatures are useful, but the storm does not become a supercell because radar sees it. It becomes a supercell because the environment allows deep, persistent rotation and separation of its internal currents. The radar merely reveals what the atmosphere has already built. The parent storm of a violent tornado is therefore a long-lived, rotating, carefully balanced thunderstorm. It feeds on warm, moist inflow, survives because wind shear keeps its updraft distinct from its rain core, and organizes its internal regions into a durable pattern. It is larger than the narrow funnel that may later descend from it, and broader than the local damage that may later mark the ground. At this point, the storm stands as a complete atmospheric engine in itself, a rotating tower sustained by the day's prepared air. Its inner core continues to tighten and deepen, but for now, the focus remains the whole storm. The supercell as the parent form that makes the later, smaller violence possible. Within the parent supercell, the most important change is no longer the existence of the storm itself, but the organization of its rotation. A thunderstorm can contain many kinds of motion at once. Air rises in one place, sinks in another, spreads outward aloft, and flows inward near the ground. In an ordinary storm, these motions may remain uneven and short-lived. In a supercell, they begin to align around a more durable center. The rotating part of the updraft becomes the mesocyclone, a deep region of organized spin inside the storm. The mesocyclone is not the tornado. It is broader, higher, and usually much wider than any funnel that may later appear below it. At this stage, the storm's inner life is best understood as a problem of rotation being gathered, tilted, and stretched by moving air. The atmosphere outside the storm already contains spin in a hidden form. Wind near the ground may blow from the southeast, while winds higher above blow from the south and then the southwest, becoming faster with height. This change in speed and direction creates horizontal tubes of rotation in the air, invisible rolls aligned roughly across the wind. They're not solid objects, only patterns of motion, but they are real. When the storm's updraft rises through this sheared environment, it tilts part of that horizontal spin into the vertical. In simple terms, the storm takes rotation that lies sideways in the surrounding air and turns it upright. This first step alone does not create a strong mesocyclone. The vertical rotation must also be intensified. That happens through stretching. When a column of air rises strongly, it lengthens. As it lengthens, its rotation can increase, much as a skater spins faster by drawing inward, though the storm process is more complex and much larger in scale. The main idea remains simple. Rising air that's already rotating can rotate faster if it is stretched upward. In the supercell, the updraft is both strong and persistent, so the tilted spin is not lost at once. It is concentrated into a deep rotating core. This is the mesocyclone. The mesocyclone often occupies several kilometers of depth and a broad area of the storm. It is not a single narrow tube. It is a rotating zone within the updraft, with pressure somewhat lower near its center than in the surrounding storm. That lower pressure helps draw air inward. The inflow entering the storm then curves as it approaches the rotating core. Warm, moist air is not merely pulled upward. It is guided into a turning path, feeding the storm in a way that supports the broad circulation. Observations show that the mesocyclone often develops first in the middle levels of the storm and later deepens downward and upward as the circulation strengthens, though the exact sequence varies between storms. The presence of a mesocyclone changes the storm's internal balance. Rotation helps the updraft resist being overwhelmed by precipitation. It redistributes pressure and alters where rising and sinking air are strongest. Rain and hail may begin to wrap partly around the rotating core rather than falling straight through it. The storm base may become more structured. The inflow becomes more focused. A region of stronger turning develops beneath parts of the storm, though at this point the circulation near the ground may still be broad or weak. The mesocyclone is therefore both a product of the storm environment and a force that reshapes the storm from within. Air entering the storm from near the ground is especially important because it contains the highest moisture and often the strongest directional turning in the wind profile. As this inflow rises into the storm, it carries horizontal vorticity, meaning spin in the environmental air into the updraft. Vorticity is simply a measure of local rotation in a fluid. Once defined, it remains plain to say that some parts of the air are more ready to spin than others. In a strongly sheared environment, the inflow can be rich in streamwise vorticity, which means the spin is aligned in a way the storm can ingest efficiently. This helps the updraft build and maintain a rotating column rather than a more chaotic pattern of eddies. The storm's downdrafts also begin to matter more at this stage. Rain-cooled air descends in parts of the storm and spreads around the mesocyclone. Some of this descending air approaches the rotating updraft from the rear or flank. The contrast between warm inflow and cooler descending air sharpens the circulation near the base of the storm. Yet the mesocyclone itself remains primarily an updraft feature. It is built by rising motion acting on environmental shear. Downdrafts help shape its lower surroundings, but the broad rotating core depends on the storm's ability to continue lifting warm, moist air through a strongly sheared atmosphere. Radar often reveals this stage clearly. Doppler measurements can show a velocity couplet, where inbound and outbound winds lie close together across the storm, indicating rotation. Over time, that couplet may strengthen and descend. Reflectivity may show curved rain and hail patterns wrapping around the rotating region. Still, radar sees a rotating storm-scale circulation, not necessarily a tornado. Many mesocyclones never produce a tornado. Some cycle through periods of strengthening and weakening. Some produce multiple tornadoes in sequence. The existence of deep rotation is necessary for the classic tornadic supercell, but it is not sufficient on its own. What makes the mesocyclone important is its depth and persistence. A brief swirl in one cloud layer does little. A deep rotating updraft that endures for tens of minutes or longer can reorganize the storm repeatedly. It can maintain a focused inflow corridor, continue stretching vertical vorticity, and create a lasting area of lowered pressure aloft and near the mid-level core. This depth also links different parts of the storm. Motion near the base is no longer independent from motion high above. The storm begins to behave more like one connected rotating system. The mesocyclone is usually not centered exactly beneath the highest visible tower. The visible cloud form can be broad, tilted, and affected by precipitation. What matters is the three-dimensional flow. Air enters, turns, rises, and accelerates. Pressure falls modestly toward the rotating core. Precipitation develops and is carried around it. Downdraft carve out nearby sectors. Under the storm base, the structure becomes more distinct, though still hidden in part by rain or distance. The storm is no longer simply a tall cloud. It is a rotating engine with an internal center of organization. At this stage, the most important transformation has already occurred. Environmental wind shear has become storm rotation. Broad hidden horizontal spin in the open air has been lifted upright and tightened within the supercell. The mesocyclone now occupies the storm as a deep, turning core, larger than any later funnel and more enduring than any brief swirl near the surface. The parent storm has moved from general organization into internal rotation, and the lower part of that rotating structure continues to sharpen beneath the cloud base. Beneath the broad rotating core of the supercell, the storm base becomes the next region of attention. The sky here is lower, darker, and more specific in form than the wide anvil and tower above. Air entering from the open plains flows inward at low levels, carrying warmth and moisture toward the storm. Some of that air remains clear for a time, especially in the rain-free inflow region, where the cloud base may appear lifted but sharply defined. Nearby, curtains of rain and hail descend from the forward part of the storm, and behind or to one side cooler descending air wraps around the rotating core. The lower storm is a place of meeting currents, where rising air, sinking air, and turning air come into close contact. The rain-free base is often the first important visual feature in this region. It forms where the storm draws in warm, moist air, but where the strongest precipitation has not yet fallen through the same column. The cloud base here may seem flat in places, because the incoming air reaches saturation at a similar height across part of the storm. Saturation means the air has cooled enough that it can no longer hold all of its water vapor as invisible gas. So condensation begins. Once defined, it remains simply the point at which cloud forms. Under favorable tornado environments, this base is often lower than in drier storms because the incoming air is rich in moisture. Even so, the base is not uniform. Parts of it rise, sag, or become textured as the storm reorganizes its flow. One of the most significant features beneath the base is the wall cloud. A wall cloud is a local lowering beneath the rain-free base, formed where air rises more strongly and cools to condensation at a lower height than the surrounding base. It is not the tornado itself. It is a lowered cloud feature attached to the storm, often beneath or near the mesocyclone. Because rising motion is stronger there, the air reaches condensation sooner, and the cloud hangs downward like a broad, uneven extension of the storm base. Some wall clouds rotate visibly, others do not rotate strongly. Some persist for many minutes, others change rapidly or dissolve. Their presence indicates focused rising motion and organization at low levels, but not every wall cloud produces a tornado. The air feeding this lowering is called inflow. Inflow is the stream of air entering the storm from the surrounding environment. Near the ground, it often moves toward the wall cloud with surprising steadiness. Leaves, grass, dust, and loose debris may all lean or stream toward the storm, showing how strongly the air is being drawn inward. This air is usually warm relative to nearby downdraft air and rich in moisture. It is the storm's fuel at low levels. The quality of this inflow matters. If it remains warm and only modestly disrupted by cold outflow, the lower storm can continue to strengthen. If rain-cooled air surges too far through the inflow region, the storm base may become undercut, more stable, and less favorable for tornadogenesis. Close to the wall cloud, the contrast between inflow and downdraft air becomes more evident. To one side, air rises and curves inward; to another, air that has been cooled by evaporation, melting, and precipitation drag descends and spreads outward or wraps around the lower storm. Evaporation cools air because liquid water changing into vapor takes up energy from its surroundings. Melting ice also cools the nearby air. These processes create downdraft regions that may feel cooler and less humid than the inflow. Where these contrasting airstreams meet, the lower storm can become sharply structured. The boundary between them is not a clean line, yet it is a real zone of interaction, and small changes there can strongly influence the next stage of development. Rotation near the wall cloud often becomes easier to see than the broader mesocyclone above. Fragments of cloud may move around the lowering. Bands of scud, which are low ragged cloud pieces, may be drawn inward and upward. Scud forms when moist air cools locally beneath the storm, often near areas of rising motion. Once defined, it remains simply detached low cloud fragments, not a tornado funnel. This distinction matters because a turbulent storm base can produce many misleading shapes. A true funnel cloud is a visible condensation feature associated with a concentrated rotating column of air extending downward from the cloud base. Ragged rising scud may resemble a funnel for a short time, but it lacks the persistent organized connection to a tightening circulation. The wall cloud itself often forms beneath the southwestern or southern part of the storm in classic Northern Hemisphere supercells, near the main inflow corridor and adjacent to the precipitation wrapping around from other sectors. Its exact placement varies with storm type and motion. What remains consistent is its connection to low-level organization. Air is rising there more efficiently than in neighboring parts of the base. Pressure may be slightly lower in the rotating area. The storm is drawing the surface layer upward into its broader rotating system. yet the circulation at this point may still be broad. The storm can appear close to producing a tornado for many minutes without doing so. Observations show that some supercells cycle through repeated wall cloud phases, with one lowering weakening and another forming later. As the lowering persists, the storm base may tighten visually. The air beneath it can become more turbulent, not in the sense of random disorder, but in the sense of many interacting eddies and strong gradients over short distance. Small cloud tags may rise and wrap around the base. The lowering may become more compact. At times, a collar-like shape forms around part of the base, though visual appearances vary greatly depending on moisture, rain, light, and viewing angle. High precipitation supercells may hide much of this region behind curtains of rain, leaving only brief glimpses of the structure. In such storms, the lower circulation can become dangerous while remaining partly concealed. The wall cloud region is also sensitive to the temperature of descending air nearby. Research indicates that tornadic supercells often maintain downdraft air that is not excessively cold when it wraps near the low-level mesocyclone. If the descending air remains only slightly cooler than the inflow, it can help concentrate rotation without completely cutting off the storm from its warm, moist surface source. If it is much colder, it may spread under the updraft too strongly and weaken the surface-based circulation. Observations support this tendency, though the exact details vary from case to case and remain an active area of study. At this level of the storm, the sky reveals that the supercell is no longer only a deep rotating tower. It has acquired a lowered center of action, the rain-free base, the focused inflow, the wrapping precipitation, and the wall cloud together show that the broader mesocyclone is pressing downward into the lowest layers of the atmosphere. The circulation is becoming more intimate with the ground, though it has not yet completed that connection. Cloud lowers because air rises faster there. Rotation becomes easier to see because the storm is concentrating its low-level flow. The open environment of the plains is now largely excluded from view. The attention rests under the storm base, where rising warm air and descending cooler air turn around one another in a tightening space of cloud and wind. The final step before a tornado fully exists is the most difficult to see clearly and the most carefully studied. Beneath the lowered storm base, the circulation that has grown within the supercell must become concentrated at the surface. This process is called tornadogenesis, the formation of a tornado. Once defined, it remains simply the moment and method by which the storm's rotating flow becomes a damaging column of air in contact with the ground. Observations show that this change can happen quickly or gradually. In some storms, a visible funnel descends toward the surface. In others, dust and debris begin to rotate at the ground first, while the condensation funnel remains higher for a time. The visible cloud is not the tornado by itself. The tornado is the rotating air column, whether or not condensation makes all of it easy to see. At the surface, the storm's inflow still matters. Warm, moist air streams inward from the open land and curves toward the low-level circulation. Nearby, cooler air from the storm's downdraft wraps around part of the circulation. Many observations and numerical studies indicate that the interaction between these air streams is central to tornadogenesis. The air descending in the rear flank downdraft, often called the rear flank downdraft air, approaches the low-level mesocyclone and can tighten the horizontal contrast in temperature, pressure, and wind. The air is not always strongly cold. In many tornadic storms, it's only modestly cooler than the inflow. This allows it to wrap near the circulation without completely cutting the storm off from its warm surface source. The exact role of downdrafts remains an area of active research, but the broad pattern is clear. Tornadogenesis usually occurs where rising inflow and wrapping downdraft air meet in a focused, Rotating region beneath the mesocyclone. Rotation near the ground may begin broadly. A wide area under the storm base can show turning motion in cloud fragments, dust, grass, or loose debris. The spin is not yet concentrated into a narrow, intense vortex. It is more like a broad turning floor beneath the storm. Stretching then becomes important again. If air near the surface is pulled strongly upward within this rotating region, the column lengthens and the spin intensifies. Pressure falls within the tightening core. Air accelerates inward and upward. The circulation shrinks in width as it gains strength. This is not a smooth mechanical process. It can pulse, wobble, and reorganize from second to second. Yet the main transformation is clear. A storm-scale low-level rotation is becoming a tornado-scale vortex. The first visible sign may be a funnel cloud lowering from the wall cloud. A funnel cloud forms when pressure drops enough within the rotating core to cool the air to saturation, producing a visible cone or tube of condensation. Because this depends on pressure, humidity, and temperature. The visible funnel does not always match the full width or full depth of the rotating air. Sometimes the condensation appears slender, while the damaging winds near the ground are broader. Sometimes the dust whirl at the surface is visible before a full funnel descends. In humid environments, the funnel may appear broad and dense. In drier air, it may remain partial or ragged, even while the circulation at the ground strengthens. At the ground, the first contact is often marked by swirling dust, soil, vegetation, and small debris. This debris cloud can develop beneath a descending funnel or independently before the funnel connects visually downward. Ground contact is the defining threshold. Once the rotating column is in contact with the surface, it is a tornado. The contact may begin weakly, with only a narrow zone of lifting dust, or it may become intense within a short time. In fields and open country, the first signs can be subtle, especially if the ground is damp or covered by vegetation that does not loft easily. In built areas, the first damage may reveal itself through snapped branches, displaced roofing, or sudden bursts of debris rising into the circulation. The flow near the surface is more complex than a simple vertical tube. Air rushes inward at low levels, curves around the center, and rises sharply. Some of it comes from the warm inflow side. Some enters from zones closer to the downdraft boundary. Friction with the ground affects this motion. Friction slows the lowest air, changes its angle of inflow, and can help produce strong convergence, meaning air crowding together into a smaller space. Strong convergence near the center supports rapid upward stretching. The ground, therefore, does not merely sit beneath the tornado as a passive surface. It shapes the lowest part of the circulation through drag, turbulence, and supply of debris. The early tornado may remain slender for a time, or it may quickly broaden. Some tornadoes begin as a narrow rope-like condensation funnel and then widen as the circulation deepens and strengthens. Others emerge already broad beneath a substantial lowering. The visual form depends on moisture, light, rain, and the detailed structure of the vortex. A tornado wrapped in rain may be difficult to distinguish, appearing more as a moving curtain or dark region within precipitation. A tornado in drier, clear inflow may stand out sharply against the sky. Appearance can mislead. Some narrow tornadoes produce intense local damage. Some broad tornadoes contain multiple smaller cores of stronger wind within a larger envelope. As tornadogenesis proceeds, the low-level mesocyclone and the new tornado remain linked. The tornado is fed by the larger circulation above and around it. It is not an isolated spinning column detached from the storm. The wall cloud may still rotate overhead. Precipitation may wrap nearby. Inflow continues to stream inward from one sector. The tornado draws strength from the storm's broader organization, and from the continued availability of air that can be stretched. If the storm's low-level structure remains favorable, the tornado can intensify rapidly. If colder outflow surges through the circulation or the storm reorganizes, the initial vortex may weaken, fail, or be replaced by another nearby. Scientists study tornado genesis with radar, mobile instruments, storm surveys, and numerical models. Yet part of the process remains uncertain because the crucial motions occur at low altitude and over short timescales. Observations indicate that strong stretching near the surface, interaction with downdraft boundaries, and a well-developed low-level mesocyclone are all important. It remains uncertain in some cases exactly how much of the near-ground rotation develops from processes descending from aloft, and how much is generated or concentrated close to the surface by boundary interactions. The evidence suggests that both are involved, with their relative importance varying from storm to storm. The atmosphere does not always choose a single path. Still, the main outcome is unmistakable. Beneath the lowered cloud base, the broad organized rotation of the supercell narrows into a surface-connected vortex. Dust rises, condensation lowers, air accelerates inward and upward. The tornado begins not as a separate event from the storm, but as the innermost tightening of the storm's existing circulation. The storm has now completed its connection from the open inflow at the ground to the deep rotating core above. What was previously a region of lowering cloud and broad turning wind has become a true tornado on the surface of the Earth. On the last day of May in 2013, the broad rotation beneath a supercell near El Reno, Oklahoma, grows into one of the most unusual tornadoes ever documented. In the record of modern observation, it stands above all others in one measure with unusual confidence. It is the widest tornado reliably documented. That statement is careful, because tornado records depend on what is being measured and how the measurement is made. For El Reno, the strongest agreement concerns width. Mobile radar and detailed post-storm analysis indicate a maximum width of about 2 6/10 miles, or a little more than 4 kilometers. That breadth is extraordinary, not only because of the number itself, but because the tornado's true circulation extends far beyond what many observers can easily see with the eye. The tornado forms southwest of El Reno from a powerful supercell moving through central Oklahoma. The day is already hostile to ordinary interpretation. The storm is large, strongly rotating and embedded in an environment of rich moisture, strong wind shear, and shifting local boundaries. Under the storm, the developing tornado does not settle into a simple cone or classic narrow funnel. Instead, it becomes a broad tornadic circulation with multiple centers of intense rotation moving within a much wider envelope. This wide structure helps explain why the tornado becomes so difficult to judge in real time. The visible condensation does not define the whole hazard. The damaging circulation extends beyond the obvious core, and the storm changes rapidly in both speed and direction. El Reno is often described as the biggest tornado ever recorded, yet that phrase requires care. If biggest means widest, El Reno is the clearest candidate in the modern record. If biggest means strongest by directly measured winds, the case becomes more complicated. Mobile radar samples winds above the ground exceeding 200 miles per hour, and some measurements higher than that are reported in the tornadic circulation. Those values are extreme. Still, they are not official surface wind measurements in the same way that direct ground instruments would provide, and tornado intensity in operational practice is rated mainly from damage. By damage survey, El Reno receives an enhanced Fujita rating of 3. That rating surprises many people because the radar-observed winds aloft are much higher than winds usually associated with such a rating. The reason is simple. The tornado spends much of its life over open country, fields, roads, and scattered structures that do not offer the kind of damage indicators needed to justify a higher official rating. The storm is physically immense, but the official rating system depends on what it strikes. This difference between radar evidence and damage rating makes El Reno scientifically important. It reveals that the official damage scale and the physical strength of the circulation are related but not identical. A tornado over open land may be stronger than its rating suggests. A tornado through dense development leaves more evidence. In El Reno, the storm's huge width and complex internal structure are better captured by mobile radar, aerial survey, and photogrammetric analysis than by damage rating alone. For this reason, it becomes a defining case in modern tornado research. It shows both how much can now be measured and how much can still remain uncertain when the circulation is broad, shifting, and only partly sampled at the surface. Its path is also unusual. Rather than moving in one steady, predictable line, the El Reno tornado changes direction and speed in ways that challenge experienced observers. The larger parent circulation turns and expands. Subvortices rotate within it. The broad envelope of the tornado is not a tidy shape laid down on the land. It pulses and bends. For storm chasers, emergency managers, and scientists in the field, this creates a dangerous mismatch between expectation and reality. A tornado that appears to be east or southeast of one point may, within a short time, expand or turn so that the dangerous part of the circulation occupies a very different area than expected. Several experienced storm chasers are killed in this event, a stark reminder that a giant tornado is not merely a larger version of a familiar form. It is a different observational problem, wider, less visually obvious in its full extent, and more difficult to escape once nearby roads and rain reduce clear choices. The width itself requires interpretation. When the record says 2 6/10 miles wide, it does not mean a solid wall of identical wind fills that whole distance. Tornadoes, especially large violent ones, contain gradients. Some parts of the circulation have stronger winds than others. In El Reno, the broad circulation includes embedded smaller vortices that move within the larger rotating field. The outer portion may contain damaging inflow and intense rotation, without always showing a dense visible funnel. The inner parts may contain the strongest local wind maxima. This means the tornado's real footprint is both broad and internally varied. A person looking only for a dark central funnel may underestimate the hazard by a large margin. Visual evidence from the event shows another important fact. The visible condensation funnel is sometimes much narrower than the full radar-defined circulation. In humid parts of the storm, condensation helps reveal the vortex, but not every part of the rotating air cools enough to become opaque cloud. Rain curtains, low cloud, and dust further distort the appearance. The tornado's visible edge can therefore seem misleadingly limited. El Reno becomes one of the best-known examples of the difference between visible tornado width and actual tornadic circulation. This difference is not unique to El Reno, but in such an extreme case it becomes especially important. It helps explain why observers close to the storm may not realize how deeply they are already inside the hazardous envelope. The tornado remains on the ground for roughly 40 minutes and leaves a damage path of many miles across central Oklahoma. It passes south of El Reno itself and near major roads, damaging homes, vehicles, infrastructure, and agricultural land. The width of the damaged swath and the complexity of the marks within it reflect the storm's internal structure. Aerial survey later reveals patterns consistent with suction vortices, small intense swirls embedded in the broader tornado that carve narrower zones of especially severe damage. At the scale of the whole storm, the tornado appears enormous. At the scale of the field, it contains smaller violent centers moving within that enormous space. Because of this event, El Reno becomes central to a more careful public understanding of tornado records. The largest tornado is not always the strongest. The strongest is not always the longest lived. The highest rating is not always the physically most intense circulation. El Reno holds the record most securely for width, and that alone makes it remarkable. Its breadth exceeds the earlier famous candidates often cited for great size, yet its scientific importance goes beyond the record book. It forces researchers and forecasters to think more precisely about what a tornado is at full scale, how radar-defined circulation relates to visible structure, and how embedded vortices within a giant tornado alter both damage and risk. In this region of the story, the tornado is no longer approached as a generic surface vortex beneath a supercell. It is approached as a measured giant, a rare case where the breadth of the circulation becomes the defining fact. El Reno shows that a tornado can occupy a landscape more like a moving field of rotation than a single narrow funnel. It remains the widest reliably documented tornado in the modern record, not because of legend, but because observations support that conclusion. Within its immense span, the storm contains shifting centers of stronger wind, uncertain visible edges, and a path that defies simple expectation. Size here means width made real on the ground, and in that measure El Reno stands alone. Once the El Reno tornado is placed at the center of attention for width, the meaning of largest becomes less simple. A tornado can be described in several ways, and each way captures a different physical reality. One tornado may be the widest, another may produce the highest wind speeds ever sampled by radar. Another may remain on the ground longer. Another may leave the longest continuous path of damage. Another may receive the highest official damage rating. These measures are related, but they are not interchangeable. A large tornado in one sense is not always large in another. To understand what the biggest tornado ever recorded means, the record must be separated into the quantities that can actually be observed. Width is the easiest place to begin because it feels visually direct. Tornado width usually means the maximum horizontal breadth of the damaging circulation at the surface or the visible tornado, depending on the method used. In modern survey practice, the best estimate often comes from combined evidence, including radar, aerial imagery, direct observation, and mapped damage. Yet even width contains uncertainty. A visible funnel may be narrower than the true damaging wind field. A damage swath may reflect only where suitable objects existed to show damage. Fields, roads, and short grass do not reveal wind in the same way as buildings, trees, or crops. In a giant tornado with multiple internal vortices, the edge of damaging wind may also differ from the edge of the strongest core. Even so, width remains one of the clearest comparative measures, and by that measure El Reno of 2013 is the leading modern case. Wind speed is a different matter. In public imagination, the strongest tornado is often assumed to be the one with the highest winds. This seems reasonable, but tornado wind is difficult to measure directly at the ground. Most tornadoes pass over places without dense instrument networks. Standard weather stations are not built to survive the strongest vortices. Mobile radars can estimate winds in the circulation, but they usually sample above the surface, not exactly at the point where the tornado interacts with buildings and vegetation. Translating those radar winds to exact ground values requires assumptions about how wind changes with height and about the internal structure of the vortex at that moment. For this reason, radar can show that a tornado contains extreme winds, but it does not always yield a single, universally accepted surface maximum. This is why official tornado intensity in the United States is based mainly on damage. The enhanced Fujita scale estimates wind speed from the effects left behind. It uses damage indicators such as houses, schools, trees, towers, and other structures, together with degrees of damage for each. The rating does not directly measure wind. It infers likely wind ranges from what was destroyed and how well those objects were built. This makes the scale practical, because damage is often the only evidence available after the storm. It also introduces limits. A powerful tornado striking open land may receive a lower rating than a weaker tornado, striking well-built structures that provide more informative damage. A badly constructed building may fail at lower wind than a strong building would require. A violent circulation passing through a field leaves fewer clues than one passing through a town. Path length is another measure often confused with size. Path length is the distance the tornado remains in contact with the ground. A very long track tornado may travel many tens or even more than 100 miles while remaining tornadic. Such a tornado is significant because it affects a large area over time and reflects a storm or storm family that remains favorable for sustained rotation. Yet path length does not automatically mean unusual width or peak intensity. A narrow tornado may travel a very long distance. A huge tornado may exist for a much shorter time. Long path length says something about duration and storm persistence. Width says something about the breadth of the surface circulation. Wind speed says something about local intensity. Damage rating says something about inferred strength based on what the tornado struck. These are related dimensions, but they are not the same dimension. Duration is similarly distinct. The time a tornado remains on the ground matters for warning, exposure, and historical memory. Some violent tornadoes last only minutes, others endure much longer. A tornado that persists for close to an hour may become famous for its extended danger, even if it is not the widest or strongest at every point in its life. Duration can also be hard to determine precisely when a tornado cycles invisibility, or when one vortex weakens and another forms nearby within the same parent circulation. Survey teams must decide whether the event is one continuous tornado or a sequence. The answer can depend on subtle evidence along the path. Damage area introduces yet another measure. A very wide tornado that lasts a long time may cover a vast total area, even if its peak winds are not the highest ever inferred. A narrower but more intense tornado may leave a smaller total area of destruction, while causing more extreme damage at the center. The public word biggest sometimes unconsciously combines width, path length, and damage area into one general impression of scale. Science benefits from separating them. When that is done, records become more precise and less mythic. Historical comparison makes the problem harder. Many famous tornadoes occurred before mobile radar, before satellite support, before modern survey methods, and before the current damage scale. Older accounts may describe a tornado as 1 mile wide or more, or as multiple tornadoes merging, or as an unbroken black mass across the horizon. Such descriptions are valuable, but they are not equivalent to modern mapped observations. A 19th century or early 20th century report may preserve genuine evidence of a giant tornado, yet the exact width, wind speed, or internal structure may remain uncertain. For that reason, modern record statements are usually framed carefully. El Reno is the widest reliably documented tornado. That wording leaves room for the possibility that earlier giant tornadoes existed without equally strong measurement. The same caution applies to the label strongest. The Tri-State tornado of 1925, the Bridge Creek and Moore tornado of 1999, the Hackleburg and Phil Campbell tornado of 2011, and others are often cited in discussions of extreme intensity. Some have extraordinary damage, some have extreme radar winds, some have exceptional path length. Observations indicate that several tornadoes in the modern era reach violent winds capable of complete destruction. It remains uncertain in many cases which single tornado should be called the strongest in an absolute physical sense, because the evidence differs from case to case and the methods are not identical. This is why the phrase biggest tornado ever recorded must be translated into a measured claim. If biggest means widest, the modern evidence points to El Reno. If it means longest path, the answer points elsewhere. If it means highest official damage rating, many tornadoes share the top category. If it means highest directly sampled winds aloft, the answer may involve cases with mobile radar measurements that are difficult to compare exactly at the ground. Science moves away from one grand label and towards several more exact ones. In that precision there is a quieter understanding. A tornado is not one number. It is a rotating atmosphere touching the ground, changing from moment to moment, measured imperfectly by damage, instruments, and memory. The record becomes clearer when each quantity is named for what it is: width, wind, path length, duration, and damage each describe one part of the whole. The biggest tornado depends on which part is being asked about, and the certainty of the answer depends on how well that part was observed. Once a giant tornado exists on the ground, the effort to understand it depends on instruments placed outside the vortex and on traces left behind after it passes. The circulation itself is too dangerous, too brief, and too variable to be sampled directly in most cases. Science therefore approaches it through measurement from around its edges. In the modern era, the most important tool is Doppler radar. Radar sends pulses of energy into the atmosphere and measures what returns after striking raindrops, hail, debris, or other targets. From that return, it can estimate not only where precipitation is located, but also how fast targets are moving toward or away from the radar. This motion information reveals rotation inside storms and inside tornadoes, yet the radar remains outside the event, translating indirect signals into a picture of the wind. A fixed weather radar sees the storm from a distance, sweeping the sky at different elevation angles. It can detect the broader supercell, the mesocyclone, and often the tighter tornadic circulation if the storm is close enough and the beam is low enough over the ground. Because Earth curves and the beam rises with distance, the lowest part of a distant tornado may remain below the radar's view. For this reason, fixed radar is often better at revealing the storm-scale environment and the mid-level circulation than the exact surface wind at a particular point. Even so, it provides one of the most valuable real-time pictures available, the classic velocity couplet, with strong inbound and outbound winds lying close together, signals intense rotation. When that couplet tightens and strengthens, it often indicates a tornado or a tornado about to form. Reflectivity is the radar product that shows the concentration and distribution of precipitation-sized targets. In a tornadic supercell, reflectivity often reveals the hook echo, a curved appendage of rain and hail wrapping around the mesocyclone. The hook is not the tornado itself. It is a sign that precipitation is being wrapped around the rotating updraft in a characteristic way. Within or near that hook, the tornado may be present. In some cases, especially large tornadoes also produce a debris signature, where lofted material from the surface appears within the radar return. This becomes especially clear with dual polarization radar, which can distinguish different shapes and orientations of targets more effectively than older systems. When debris is lofted high enough and sampled clearly, Radar can indicate that the circulation is not only rotating but actively striking the ground and lifting non-meteorological material into the air. Mobile Doppler radar brings the instrument closer. These vehicles are driven into the field to sample storms at much shorter range, allowing finer spatial detail and lower beam heights over the tornado. This is how some of the most striking measurements of tornado wind have been obtained. Close-range mobile radar can reveal the breadth of a circulation, the intensity of smaller embedded vortices, and the change in wind speed across very short distance. In the El Reno tornado, mobile radar is central to establishing its remarkable width and to documenting extremely strong winds within the circulation. Yet mobile radar also has limits. It samples the air above the ground, not necessarily the exact wind at the surface. The storm may change between scans. Rain, debris, and geometry complicate interpretation. The measurements are powerful, but they're still measurements through a moving atmosphere rather than inside a fixed controlled experiment. Visual observation remains important, though it is often less exact than instruments. Photographs and video can reveal the visible funnel, the debris cloud, the motion of subvortices, and the changing shape of the tornado. By comparing images from different locations and times, researchers can perform photogrammetry, the use of photographs to estimate size, distance, speed, and geometry. This approach has helped reconstruct some famous tornadoes in detail, especially when multiple views are available. Even so, visual evidence can mislead if the tornado is rain-wrapped, partly condensed, or much broader in circulation than invisible cloud. A giant tornado may hide its true edge, and the eye naturally seeks a central dark core rather than the full wind field. After the storm passes, the ground becomes another instrument. Damage surveys examine what the tornado did to buildings, trees, vehicles, towers, crops, and terrain. Survey teams map the path, identify zones of different damage intensity, and assign an official rating based on damage indicators. This work requires care because damage reflects not only wind, but also construction quality, object orientation, debris impacts, and local topography. A well-built structure can survive winds that destroy a poorly built one. A tree may fall because of root weakness as much as trunk failure. Still, over many cases, careful survey practice provides a workable method for estimating the lower bound and likely range of tornado wind at the surface. Aerial and satellite imagery extend the survey view. From above, the damage path may show subtle patterns not easily visible on the ground. Swaths of flattened crops, spiral marks in fields, convergent treefall, and narrow streaks of exceptional destruction can all reveal the structure of the tornado. In giant tornadoes, aerial imagery is especially useful because the path may be very wide and internally complex. Smaller, intense vortices can carve narrow streaks within a much broader damage area. These patterns help scientists distinguish the general envelope of the tornado from the most violent internal cause. Field instruments placed deliberately in tornado-prone regions have occasionally provided additional information. Probes designed to survive near or within a tornado can measure pressure, temperature, humidity, and wind if the vortex passes over them. Such direct encounters are rare, but they have offered valuable evidence that pressure can fall sharply in the core and that wind changes rapidly over small distance. Because the chance alignment required is unusual, direct in situ measurements remain limited. Most tornadoes are still known mainly through radar and damage rather than through instruments placed directly in their path. Debris itself becomes a measurable part of the event. Large tornadoes lift leaves, branches, soil, insulation, wood, metal, and many other materials into the air. This debris affects visibility and can influence radar signatures. It also changes the hazard, because wind in the tornado is no longer acting alone. Fast-moving debris becomes a source of impact damage that can destroy windows, walls, and vehicles even where the wind alone might not fully do so. In the science of observation, debris is both a marker and a complication. It confirms surface contact, yet it can obscure the true flow and introduce additional danger for researchers and the public alike. No single observing method is complete. Radar sees motion aloft and sometimes near the ground, but not always the exact surface wind. Damage surveys show the ground truth of what was struck, but only after the event and only where objects existed to be damaged. Photographs show visible form, but not the entire circulation. Probes are rare and brief. Each method captures one region of the tornado's reality. The most reliable understanding comes when they are combined. A radar couplet aligns with a debris signature. Video shows a broad condensation funnel and moving subvortices. Ground survey maps a wide damage path with streaks of extreme destruction. Together, these pieces reveal a tornado that no single viewpoint could fully describe. At this stage, the focus remains outside the vortex itself. The giant tornado is approached through echoes, motion estimates, visual records, pressure traces, and scars on the landscape. Science circles the event and reads it from its effects and reflections. The result is a careful outer map of something too intense and too brief to hold directly. In that map, the tornado begins to show not only as a destructive force, but as a measurable flow with broad structure, inner variation, and evidence scattered through air, instrument, and land. Around the core of a giant tornado, the air does not move as one smooth cylinder. It forms a broad circulation with layers, gradients, and changing paths that depend on distance from the center, height above the ground, the supply of inflow, and the influence of the parent storm. The familiar image of a funnel suggests a single downward pointing shape, but the actual flow is wider and more varied. Air near the ground accelerates inward from the surrounding environment. As it approaches the tornado, it bends into a tighter curve around the center and then rises rapidly. Above, that rising air continues into the lower part of the storm and remains connected to the larger rotating circulation of the supercell. The tornado is therefore not only a spinning column, it is a moving zone of inward flow, curved motion, upward acceleration, pressure change, and suspended debris. One of the first important features is inflow at the surface. Outside the visible condensation, the air may already be moving strongly toward the tornado. This inflow can extend far from the center, especially in a large tornado embedded within a major supercell. Grass may lean inward, loose soil may begin to lift, small objects may slide or tumble before the main vortex arrives. The air at this stage is not simply rushing straight forward. Because of the tornado's rotation and the larger storm circulation around it, the inflow often follows a curved path. It spirals inward, moving faster as it approaches the center. This means the tornado influences a broad area beyond the visible funnel or debris cloud. The hazardous region begins well outside the darkest or most obvious part of the storm. As the air moves inward, the pressure generally decreases toward the core. Pressure in a tornado is lower than in the surrounding air because the rotating and rising flow helps maintain a central region of reduced pressure. The pressure drop is real, but it is often misunderstood. Buildings are not usually destroyed because they explode outward from pressure alone. The main destructive force is wind acting on structures and on debris, though rapid pressure changes can contribute in some cases, especially when combined with structural weakness and openings. Measurements from rare direct observations confirm that pressure can fall substantially within tornado cores, but the precise magnitude varies greatly from case to case and is difficult to sample at the moment of strongest winds. What remains clear is that the pressure drop helps support the inward acceleration of air toward the centre. The wind field around the core has two main components. One is tangential wind, the air moving around the centre. The other is radial wind, the air moving inward toward the centre. Once defined, these terms can remain plain in meaning. Tangential wind circles, radial wind approaches. In a tornado, both are present. The balance between them changes across the vortex. Farther out, the inflow component may be easier to recognize as air streams inward across the land. Closer to the center, the rotational component grows stronger, and the path of the air becomes more sharply curved. The combination produces a spiral rather than a simple ring or a straight rush. Near the very center, upward motion becomes especially important as the air is forced into a tighter and faster ascent. The upward motion is essential because a tornado is not a surface world detached from the sky. The inflowing air does not merely circle, it rises into the storm. This ascent helps stretch the rotating column and maintain strong winds. It also carries debris upward. Leaves, dust, fragments of wood, insulation, and other material become suspended in the circulation, sometimes reaching great height. In a giant tornado, the debris field can be enormous and internally uneven. Heavier objects may remain near the lower part of the vortex or be thrown outward after partial lift. Lighter material can rise much farther and become spread downwind into a wider cloud. This debris is not only a byproduct, it changes visibility, alters radar signatures, and increases destructive power through impact. A large tornado often contains a broad outer circulation and a more intense inner region. The outer circulation may already be capable of damaging structures, uprooting trees, and overturning vehicles. Inside that envelope, winds may strengthen dramatically over a much smaller distance. This is one reason giant tornadoes are difficult to judge by appearance alone. The edge of condensation may not correspond neatly to the edge of damaging wind, and the strongest winds may occupy only part of the broad visible mass. In El Reno and in other large tornadoes, observations show a wide rotating envelope with more intense embedded zones. The air around the core is therefore not uniform. It contains bands, surges, and local maxima moving within the larger vortex. Surface friction also shapes the flow. The ground slows the lowest air and changes its angle as it enters the tornado. Over smooth wet fields, rough grassland, paved roads, wooded areas, and developed neighborhoods, the exact interaction changes. Friction tends to increase convergence near the surface by slowing the air and allowing more inward turn. This can strengthen upward stretching in the lowest layers. At the same time, friction also produces turbulence, meaning irregular eddies and mixing on many scales. Once defined, turbulence remains simply uneven, swirling motion superimposed on the broader flow. In the tornado, turbulence is intense near obstacles, among debris, and where different parts of the circulation interact. Yet the overall vortex remains organized enough that the main inward, rotational, and upward structure persists through that disorder. The core itself may not be empty in the ordinary sense. Popular imagery sometimes suggests a hollow center, but the interior of a tornado can range from partially clear in some small vortices to densely filled with cloud and debris in larger ones. The central pressure minimum, where present, is still a region occupied by moving air. In giant tornadoes, dust and debris often make the lower core opaque. Higher up, condensation may wrap around the circulation in layers of varying thickness. Rain from the parent storm may also mix into part of the vortex. The result is often a dark, shifting interior where visual boundaries are poor guides to the true wind field. The parent storm continues to influence everything around the core. Rain-cooled downdraft air may wrap around one side of the tornado. Warm, humid inflow may dominate another side. This means the tornado is often asymmetric, not perfectly balanced in all directions. One sector may contain stronger inflow. Another may be filled with heavy debris and precipitation. Another may have the sharpest local wind gradient. Such asymmetry is important in giant tornadoes because it affects both motion and damage. The tornado may seem broader on one side, more obscured on another, and more violent in local pockets that shift with time. Within this broader circulation, soundings from radar and damage patterns suggest that the tornado can pulse. Its diameter may expand or contract. Winds may strengthen in one sector and weaken in another. The pressure minimum may deepen and then relax. None of this means the tornado loses its identity. It means the vortex is a living atmospheric structure, continuously fed by changing inflow and shaped by the storm-scale circulation around it. The flow around the core is therefore dynamic rather than fixed. A giant tornado is not a stable machine turning at one constant speed. It is a moving field of inward rushing, curving, rising air, with debris and pressure change woven through it. At this region of the story, the tornado is understood less as a visible object and more as a circulation pattern. Air comes inward across the land. Pressure falls toward the center, rotation tightens, upward motion lifts air and debris into the storm. The outer envelope may be broad and already dangerous, while the inner parts contain stronger, more concentrated winds. Around the core, the flow is layered, uneven, and deeply connected to the parent supercell above. The tornado's true body is this pattern of motion, wider than its funnel, more complex than its outline, and still becoming finer toward its innermost structure. Inside a giant tornado, the broad circulation is often not the smallest meaningful unit of motion. Within that wider rotating body, smaller concentrated vortices can appear and move. These are called subvortices, sometimes also called suction vortices, when they leave narrow streaks of especially intense damage. Once defined, they remain simply smaller spinning cores embedded within the larger tornado. They do not replace the main vortex. They exist inside it, orbiting, merging, intensifying, or fading as the parent circulation continues. In some of the most violent tornadoes ever studied, these smaller vortices are central to the pattern of destruction. They help explain why damage within one tornado path can vary so sharply over very short distance. A broad tornado may give the impression of one continuous field of wind, and at one level that impression is correct. The whole circulation is dangerous. Yet within that field, the air can organize into tighter pockets where rotation becomes especially strong. These subvortices may be only a small fraction of the width of the main tornado, but their local winds can exceed those in the surrounding flow. As they move within the larger vortex, they produce swaths of extreme damage that cut across a broader area of less severe destruction. In fields and forests, these paths may appear as narrow strips of stripped vegetation or sharply convergent marks. In towns, they may appear as concentrated corridors where well-built structures are swept away, while buildings a short distance away, though still badly damaged, retain more of their walls or framing. The reason smaller vortices can become so destructive lies in concentration. The broader tornado already contains rotation, inward motion, and upward stretching within that environment. Local instabilities and interactions can tighten the flow further into narrower cores. When the diameter of a rotating feature decreases while strong stretching continues, the local wind can rise sharply. The physics follows the same general principle seen at larger scales, but now it acts inside the tornado itself. A vortex within a vortex is stretched, fed, and turned by the broader circulation around it. The result is a compact region of exceptionally intense wind. These subvortices are not always steady in number or position. In some tornadoes, only one or two are clearly identifiable at a time. In others, several may be present, revolving around a common center. They can form near the edge of the main condensation funnel, within the debris cloud, or in parts of the circulation that remain partly hidden by rain and dust. Their motion is often rapid because they are being carried by the larger rotating flow while also spinning around their own smaller centers. To an observer, the visual effect can be confusing. Dark tendrils, dust whirls, and rotating columns may seem to appear and vanish around the main tornado. Some of these are genuine subvortices. Others may be transient debris plumes or condensation features without a fully developed core. The distinction is not always easy to make in real time. Radar and post-storm damage analysis help reveal these smaller structures more clearly. High-resolution mobile radar can sometimes detect concentrated wind maxima embedded within the larger circulation. Aerial surveys may later show narrow, sinuous streaks of more intense ground scouring, tree fall, or structural damage. These marks are among the strongest clues that the giant tornado did not act as a uniform ring of wind. Instead, it contained compact centers of greater violence moving within the wider path. In some historical cases, reports of houses swept completely away beside others, left partly standing, may reflect this same process, though construction quality and debris impact also matter. The atmosphere rarely leaves a single clean signature, but recurrent narrow damage swathes are strong evidence of subvortex activity. The presence of multiple vortices also helps explain some of the most deceptive behavior of giant tornadoes. A broad tornado may seem to move in one direction overall, while individual subvortices move through a location in a more complicated pattern. One place may be struck by the outer circulation, and then, moments later, by a much more intense embedded core. Another place may lie within the broad damage path yet avoid the strongest small-scale vortex. To someone on the ground. This means the tornado's danger is not evenly distributed or easily inferred from its visible center alone. The whole circulation remains a threat, but the highest local winds may arrive in smaller rotating pockets that are difficult to anticipate by sight. Subvortices also interact with debris in distinctive ways because their winds are especially strong. They can loft heavier material and accelerate debris more violently than the surrounding flow. This amplifies damage through impact. A house or vehicle struck by wind already experiences great force, but when that wind also carries dense fragments of wood, metal, masonry, or vegetation, destruction increases. The smaller vortex becomes not only a region of stronger air motion, but a region of concentrated debris bombardment in large tornadoes crossing developed land. This effect can become severe. The tornado feeds on the material it has already torn loose, and the embedded vortices become moving centers of both wind and impact. There is still uncertainty about exactly how subvortices form in every case. Observations indicate that strong low-level rotation, rapid stretching, and instability within the larger tornado all contribute. It remains uncertain whether every giant tornado must pass through a similar internal sequence, or whether different storms produce smaller vortices through somewhat different pathways depending on humidity, downdraft structure, surface friction, and the detailed shape of the parent mesocyclone. Numerical simulations support the idea that multiple vortex structure can emerge naturally when a strong tornado reaches certain internal states. But the atmosphere does not always offer full direct confirmation at the moment of transition. The evidence is strong that subvortices are common in large violent tornadoes. The exact microscale evolution remains harder to observe. In visual terms, a multiple vortex tornado may appear as a broad funnel with smaller rotating appendages, or as a wide dirty mass with separate whirling columns visible around its perimeter. At other times, the smaller vortices remain hidden within dust and debris, known mainly from the damage they leave. This hidden nature is important. The most intense local winds in a giant tornado are not always visible as the darkest or most dramatic part of the cloud. The true centers of greatest destruction may be concealed inside a wide, opaque envelope. This makes close-range judgment unreliable and contributes to the exceptional danger of giant tornadoes like El Reno, where the circulation already extends far beyond the obvious core and the internal strongest pockets move within it. At the microscale, then, the tornado becomes a society of rotating structures rather than a single simple tube. The broad vortex still governs the whole. It provides the envelope of inflow, pressure drop, and rising motion. Inside that envelope, tighter cores emerge and revolve. They carve narrow paths within broad ruin. They concentrate wind, lift heavier debris, and create abrupt changes in damage over distance small enough to fit within a street, a field margin, or a stand of trees. The tornado's innermost violence is often found here, not in the average wind across its full width, but in the sharper, smaller vortices moving within the giant. In this deepest visible layer of structure, the great tornado resolves into many smaller turning centers, each temporary, each intense, and each part of the broader storm that contains them. At the innermost scientific boundary of a giant tornado, observation reaches a limit. The broad environment can be mapped, the parent supercell can be tracked, the mesocyclone, wall cloud, surface vortex, outer circulation, and embedded subvortices can all be described with increasing precision. Yet at the very center of the most violent flow, knowledge becomes narrower and more conditional. A tornado is a short-lived atmospheric structure, changing from second to second, often wrapped in rain, dust, and debris, with the strongest motions occurring close to the ground where instruments are least likely to sample directly. Science can define much of its form. It can estimate much of its wind. It can still only partly resolve the exact state of the core at the moment of greatest intensity. The central pressure drop is one of the clearest examples. Observations from rare direct probes and indirect analysis indicate that pressure falls substantially within strong tornadoes, sometimes very sharply over short distance. This lower pressure is a genuine feature of the vortex and contributes to the inward acceleration of air. It remains uncertain, however, exactly how deep the pressure minimum becomes in the strongest giant tornadoes at their most intense moments. The problem is not a lack of theory alone. It is mainly a problem of measurement. Few instruments survive direct passage through the most violent core, and fewer still are positioned exactly where the central minimum passes. As a result, science knows that the pressure can drop rapidly and significantly, but often cannot specify the deepest value in the most extreme cases with full certainty. The exact peak wind at the surface is similarly elusive. Mobile Doppler radar has transformed tornado science by revealing very high winds within tornadoes, including giant ones. These measurements are among the best evidence available for internal structure and intensity. Yet radar usually samples at some height above the ground, the lowest tens of meters, where buildings, trees, soil, and vehicles experience the full force of the tornado, remain more difficult to measure directly. Wind in a tornado can change sharply with height, especially near the surface where friction, debris, and convergence alter the flow. Because of this, a wind sampled aloft is not automatically identical to the wind at the ground below. Scientists can estimate, compare, and infer. In many cases, it remains uncertain what exact surface maximum occurred at the tornado's strongest instant. Even the shape of the innermost core is variable. Some tornadoes appear to have a narrow central zone of strongest rotation. Others broaden into a larger core or contain several tight maxima revolving within a wider envelope. In giant tornadoes, the central region may not be one cleanly bounded space. It may be a constantly evolving arrangement of subvortices, pressure dips, surging inflow, and debris-filled circulation. This means the center is not always a single point to be found and fixed. It can shift, split in effect, or become partly obscured by the larger structure around it. A tornado can therefore be highly organized at storm scale, and still internally irregular at microscale. Debris adds another layer of uncertainty. Once a violent tornado begins lifting large amounts of material, the airflow is no longer only air and cloud droplets. It includes wood, metal, insulation, leaves, soil, gravel, fragments of buildings, and in some cases much heavier objects. This debris changes the observational problem. It hides visibility. It complicates radar returns. It creates dangerous impact zones that prevent close direct measurement. It may also alter the flow locally through drag and mixing, though the degree of that influence in the strongest cores remains an area of continuing study. Observations indicate that debris loading matters, especially in large damaging tornadoes, but it remains uncertain exactly how much it changes the peak dynamics of the core in each case. The lowest few meters above the surface are especially difficult to understand. This thin layer is where the tornado meets the land, where friction is strongest, where grass and soil begin to move, where buildings either hold or fail, and where the broad circulation converts into direct damage. It is also where models and radar have the greatest difficulty resolving the finest details. Surface roughness changes from field to road, from road to tree line, from tree line to town. A tornado crossing open prairie experiences one kind of drag. The same tornado entering a neighborhood meets another. The difference affects inflow, angle, turbulence, debris generation, and local wind concentration. Science understands the importance of these effects in principle. The exact behavior of the core over each kind of terrain remains harder to specify in real time. Another limit involves time itself. A tornado does not reach one fixed final state and hold it. The inner circulation pulses, subvortices intensify and weaken, the diameter expands and contracts, the path bends. The relation between visible funnel, debris cloud, and strongest wind shifts from 1 minute to the next and sometimes from 1 second to the next. Any measurement captures only a moment. Any damage survey reflects only what happened where vulnerable objects stood. Any video frame reveals only one angle through cloud, dust, and rain. The core is therefore known not as a single frozen truth, but as a sequence of partial glimpses gathered from different methods and then carefully combined. This limit does not mean ignorance. Science has established a firm framework. Giant tornadoes form within supercells in environments of strong instability and wind shear. Their low-level circulation tightens beneath a mesocyclone. Their broad wind field contains inward flow, tangential rotation, upward motion, and often subvortices. Their width can be measured. Their paths can be mapped. Their radar signatures can be analyzed. their damage can be surveyed. El Reno remains the widest reliably documented tornado in the modern record because the combined observations support that conclusion. Other tornadoes may rival it in peak wind, path length, or total destruction. But those are separate measures and often less directly comparable. The limits lie not in the broad structure, but in the most exact values at the deepest center. At the core, then, the scientific picture becomes one of bounded certainty. Observations indicate that the strongest winds occur in very confined regions, often within sub-vortices. Observations indicate that pressure falls markedly toward the center. Observations indicate that the core evolves quickly and interacts strongly with surface roughness and debris. It remains uncertain, in many cases, what exact peak wind touches the ground, what exact minimum pressure occurs at the lowest point, and how the finest internal transitions unfold from second to second. These are not failures of understanding. They are the remaining edges of measurement in a phenomenon too violent and too brief to be held still. The story has now moved as far inward as observation can follow, from planetary heating to continental geography, from air masses to boundaries, from storm environment to supercell, from mesocyclone to wall cloud, from tornado birth to giant width, from outer circulation to embedded smaller vortices. The path narrows into the deepest measurable center. There the tornado remains partly known and partly hidden, a rotating atmosphere that yields much to instruments, and still keeps some of its sharpest details beyond complete capture. The great tornado now recedes into distance and measurement. What remains on the land is a path, a set of marks where air once moved with unusual force. What remains in science is a clearer outline of how such a storm belongs to larger patterns of Earth. Warm seas feed moisture into the lower atmosphere. Broad plains allow air masses to travel and meet. Boundaries gather contrast. A supercell grows, rotates, lowers, and tightens. At the ground, the vortex forms, widens, and carries smaller centers of stronger motion within it. Each layer connects to the next. Nothing in the process stands alone. The widest reliably documented tornado in the modern record remains the El Reno tornado of 2013. That conclusion rests on observation, not on legend. Yet even there, the deepest center is not fully fixed in every detail. The atmosphere allows close study, but not complete possession. Radar sees much. Damage reveals much. The storm itself passes quickly, leaving scientists to assemble its form from traces in air and on the ground. In that work there is a quiet kind of patience. A tornado is neither a mystery without structure nor a machine known in every part. It is a natural event shaped by heat, moisture, motion, and terrain, and sharpened by timing. Its greatest violence appears at the smallest scales inside a broader circulation. Its widest form can cover open country like a moving field of wind. Its strongest moments may remain only partly measured. By the end, the sky clears, the inflow ceases, and the rotating column loosens back into ordinary air. The land remains, the plains still open beneath the same atmosphere that produced it. Above them, sunlight, moisture, and wind continue their slow exchange, calm in appearance, exact in process, and never fully still.